All right, we have the fire hose problem, where we have a fire hose that shoots water, so it's got to be blue, all right, at a velocity of 25 meters per second at an angle of 35 degrees above the horizontal, okay? The question is, where does the fireman want to stand so that the water, how far away from the building, in other words, what's our delta X, right? So that, from the building, so that the burning building my baby. All right. So that the burning building, so that the water goes up and basically hits it at the top of its arc. Is that correct? Okay. So it's sort of a max height problem, right? But we're not asked for the max height. We're asked for how far away he should stand so that it happens to be at that max height. Okay? So how does anybody got any ideas on how to approach this problem? Well, let's start with what we can write down. Okay, we'll write down what we know. So there's our D for doofus. Now the knowns and the unknowns. For projectiles, we're going to use that double barrel table, right? So we know that V naught is equal to 25 meters per second at an angle theta is equal to 35 degrees. So here's our double barrel table here. We got the X stuff, we got the Y stuff. And V naught, we know, is going to be V naught cosine theta for X and V naught sine theta, good, for Y. And then what's the other thing that's always the same? Acceleration. Acceleration in the X direction, 0 in the Y direction, negative G. Okay? So it seems to me, what else do we have? Deltas, right? We don't know what delta Y is, but we want it to be delta Y max, don't we? All right? So we know delta Y max, and that's going to give us a clue about something, isn't it? All right? And we know the delta X is what we're looking for. Okay? Are we going to use time? I don't know. Time's the bridge. We may as well write it in there. And so we'll say we know the time is going to be the same for each, right? All right. So delta Y max actually gives us one little extra bit of information down here, and that is V at the time it hits. That's exactly right. Vy at the time it strikes that building is going to be equal to 0. All right? So now we've got V naught, we've got acceleration, and since we know our delta Y is delta Y max, we know that Vy is going to be equal to 0. So let's write down what we really have. We've got Vy, V naught Y. We've got Vy equal to 0. We've got acceleration as negative G. And if we wanted to solve, could we solve for time now? What would we use? We would use, I'm hearing it, yes, it's VOTAC. All right, so we know that, let me scroll up a little bit here. We know that Vy is going to be equal to V naught Y minus GT. I just wrote VOTAT with our Y parameters already plugged in there. Okay, we know this is equal to 0, right? Fruit Ninja. All right, so now we know that V naught Y is equal to GT. Solving for T, we get T is equal to V naught Y over G, or V naught sine theta over G. How does that help us? Exactly. We can get how far away the water will be at that time. Okay? And which equation will we use for that? All right, well, let's take a look at what we got in the X direction. We have acceleration, we have Vx. We want to know what delta is, and now we have an expression for time. Okay? There's the meat grinder equation. So working in the Y direction, I'll use red, and we'll say that delta, that is not red. I just did Y anyway. This actually doing X, but I'll switch colors. So delta X is equal to Vxt plus 1/2 Axt squared. Fruit Ninja. All right, so delta X is just equal to Vxt. So our delta X is going to be equal to, Vx is, anyone? V naught cosine theta. All right, that's our Vx. All right, look, right here. That's our Vx. Whoops. Our Vx is V naught cosine theta, and our T was V naught sine theta over G. That looks like a negative sign, but it shouldn't be there. So we got times V naught sine theta, and all of that over G. All right, so I'm going to do a little bit of a trig trick here, okay? A tricky trig trick, all right? And that is, we're going to say delta x is equal to, I'm going to multiply the top and the bottom by 2, all right? And what I'm going to do is I'm going to say V naught squared, right? I'm taking V naught times V naught. I'm going to multiply the top by 2, so I've got 2 sine theta cosine theta, and since I multiplied the top by 2, I'm going to multiply the bottom by 2 times 2g. Exactly. So 2 sine theta cosine theta, we use our tricky trig function, or trig identity, V naught squared sine 2 theta over 2g. Now, does that look familiar? Doesn't that look like the range equation? But what's different about the range equation? The range equation doesn't have the 2 in there, right? Doesn't that make sense? Well, we're looking for this parabola right here. So when it's the total range, what we're getting is 1/2 of the original range, right? That 2 in the denominator means 1/2 the range. So we can see that since this right here, the total range, delta x, we know from the range equation is V naught squared sine 2 theta over g. If we take 1/2 of that, this part right here, that just gives us V naught squared sine 2 theta over 2g. We just multiply that through, and that's exactly what we got. So now let's go ahead, go back up here, plug in the numbers that we had for that. So our delta x, that's the distance the fireman wants to stand away from the wall, is going to be equal to, V naught is 25 meters per second. We're going to square that, times the sine of 2 times 35 degrees is 70 degrees, divided by 2 times 9.8 meters per second squared. And whoop, got a squared, and I knew that because I was doing a dimensional analysis. We got meters squared per second squared divided by meters per second squared yields meters. So we got what we want right there. And so plugging in all those numbers, we get a final answer. Delta x is equal to 29.96 meters. And in where we live, that's equal to delta x is equal to 30 meters. So the fireman should stand 30 meters away so that if he aims his hose at 35 degrees with a velocity of 25 meters per second, it will be at its highest point if he's standing 30 meters away.